Dear student, welcome to my channel. Topic of this video is RSA algorithm. This is the second part of the RSA. In this video, I am going to explain additional exercises. Now directly start with the exercises. P equal to 5, Q equal to 13, E equal to 7, that is nothing but public key. Plain text is 9. Perform RSA encryption and decryption. We calculate N as P into Q, that is 5 into 13 is equal to 65. Phi of n is nothing but 5 minus 1, 13 minus 1, because P and Q are prime number. So when number is prime, Euler torsion function is nothing but that number minus 1. So therefore it is 5 minus 1 into 13 minus 1, which is equal to 48. Now E equal to 7, that is nothing but the public key. Now we require to choose the private key. So all these operations are performed at the receiver side when sender want to send the message to the receiver. Now here we first calculate the private key of the receiver, and there is a relationship between the private key and public key in such a way that D into E congruent to 1 mod phi of n, or D and E are a multiplicative inverse of each other. To calculate this D, we require to find out, or we require to use extended Euclidean, that is of 7 and 48. Now I have already published the video on extended Euclidean, so 7 48. So we'll write 48, 7 6 plus 6. 7 is equal to 6 into 1 plus 1. 6 is equal to 1 into 6 plus 0. Now here 42 plus 6, 48. Then this 7 comes here, this 6 comes here, this 6 comes here, this 1 comes here. Now we will not take this equation because it equate to 6 equal to 1 of 6. So we will start from this equation. So arrange these two equations, and with the back substitution we are doing the process. So I am not going to explain again in this video. So you just refer my previous video to understand how to calculate the multiplicative inverse. So when we use a reverse substitution or back substitution operation, we are getting the D equal to 7. So D equal to 7 is our private key. Now public is 7. So 7 into 7 is what? 49. And 49 is congruent to 1 mod phi of n. So when we subtract 49 minus 1, which is divided by 48, so this equation gets satisfied. Then next step is the encryption. Now encryption is performed at the sender side on the message, in which it uses the public key of the receiver. Therefore C is equal to m raised to e mod n, that is nothing but C equal to 9 raised to 7 mod 65. Now at the sender side we don't know the P and Q, we know only the N, because here this P and Q are decided at the receiver side, and only it will send the public parameter, that is nothing but N and E to the sender. Now we can calculate 9 raised to 7 mod 65. So here we can calculate directly also, and if we want we can use the square and multiply algorithm. So it is a systematic approach. I have already published the video on this also. You just refer that video to understand this operation. Now decryption is nothing but the it's exactly the formula is same, only the change in that in the encryption we use the public key, and in the decryption we use the private key, and this and M and C position get exchange. Now again it is 9 raised to 7 mod 65. Now here, and it is a center point, so for the same we are getting the same encryption and decryption value. So this equation is for encryption, and for decryption also we are getting the same value, so we can directly copy the answer from here. So here in this case that encryption and decryption value is same. Now we'll see the next example. P is equal to 7, Q equal to 70, is 5, M equal to 4. So first we calculate the N, which is nothing but P into Q, that is nothing but 7 into 17, that is 119. After that we calculate the phi of N, which is 7 minus 1 into 17 minus 1, which is equal to 96. Now E is equal to 5 and M equal to 4. Now after that we perform the calculation for D, that is nothing but T into E congruent to 1 mod phi of N. Then here E is 5 and we require to calculate the D, so which is nothing but the multiplicative inverse. So therefore we calculate this using the extended Euclidean, and we require to calculate the extended Euclidean for 5 and 96. So 96 is equal to 5 into 19, 95 plus 1. 5 is equal to this 1 into 5 plus 0. So here we can't take this equation because it is equal, so we take 19 minus 5. Now here we require to find out the with respect to 5. Now with respect to 5 our answer is what, minus 19, but we take the positive value. So for that positive we just take 96 because mod operation is with respect to 96. So on this also I have published the video how to calculate the mod of negative number. So therefore d is equal to 96 minus 19 is equal to 77. So here the private key is 77. Now encryption is equal to c raised to m raised to e mod n, c equal to 4 raised to 5 mod 119. So this operation is very easy, so we can directly calculate. So z, this is square and multiply operation, 4 raised to 5. So 5 is represented in binary and we take from MSB to LSB, and in the systematic way we can calculate 4 raised to 5 mod 119. So our encrypted value is 72. Now we require to perform the decryption, and for decryption we use this formula, that is m equal to c raised to d mod n. Now our c is 72, our private key calculated is 77 and mod 119. If we see these numbers are large and it is very difficult to calculate, so better way is to use the Chinese remainder theorem. So with the help of Chinese remainder theorem we can easily solve the problem. Now how to apply the Chinese remainder theorem I will explain step by step. Now generally we apply the Chinese remainder theorem when this exponent and this number is very large. So before applying the Chinese remainder theorem we calculate dp is equal to d mod p minus 1. This is p minus 1 and this is q minus 1. This is q minus 1. Now here the p and q, see the example, p is 7 and q is 17. So here p minus 1 is 6, 77 mod 6 is equal to 5, and d mod q minus 1, q is 17. So 77 mod 16 is equal to 13. So first we calculate this, then we change our equation, that is mp is equal to c raised to dp mod p, and mq is equal mq is equal to c raised to d q mod q. Now c is nothing but our 72. Now dp change from 77 to 5, and here instead of 119 we are using the parts, that is nothing but 7. So that's why Chinese remainder theorem we can apply at the decryption side, because at the decryption side receiver knows what is the p and q value. At the encryption side we can't use the Chinese remainder theorem. Now here the equation for mp becomes 72 raised to 5 mod 7. So compared to this equation it is very easy to calculate. So here again we can use the square and multiply algorithm, or we can directly calculate. After that for mq, c is 72 and 77 mod 16 value comes as a 13. So for that we can use the square and multiply algorithm, and 13 is nothing but 1101, and in this way we can perform the operation. So here we are getting the final equation for Chinese remainder theorem is this equation, and this is for the second equation, that is mp is equal to 4 and mq is equal to 4. So equation becomes x is equal to, it is basically congruent, x congruent to 4 mod 7, because this answer comes as 7, and this with respect to this mod 7 is there, and here 4, and with respect to mod 17, 4 mod 7 and 4 mod 17. So here there is no need to solve the problem, because the by default answer is what, 4. So in this way we can get the our original text. So this is the way that m equal to 4, that 4 gets converted to 72, and 72 again gets converted to 4. So in this way we can solve the problem. Now see the next problem. P is 7, Q is 11, E 13, and plain text is 15. So now we will solve the problem. Again step n is 77, phi of n is p minus 1 q minus 1, which is equal to 60, is equal to 13 given, and plain text is 50. Then first we calculate the private key of the receiver side. Now d into e is 1 congruent to 1 mod phi of n. So we calculate the inverse. So for that we require to calculate the extended Euclidean for 13 and 60. So here we can write down the equation. 60 is equal to 13 fours of 52 plus 8. In this, whatever in quotient, whatever in bracket, they are nothing but the coefficient. So in this way we will contact this equation, arrange this equation, and using the back substitution procedure we will follow. So here whatever in bracket, they are the coefficient, and without bracket all are nothing but variables. So we substitute the value of variables. We can't take this equation, we will directly start from this equation. So it is very easy to calculate. So here answer came as a minus 33. So again minus mod answer comes, again we make the positive. So that is nothing but 60 plus 60 minus 23 is equal to R. So private key is 37. Now we perform the encryption. So encryption is compared to costly than the decryption, because at the decryption we can use a Chinese remainder to simplify the operation. So therefore C is equal to 15 raised to 13 mod 77. We can apply the square and multiply algorithm, and by that way we get the cipher text as a 64. Now again we apply the decryption to get the original text. Now our text is cipher text is 64, D get 37 raised to mod 64 raised to 37 mod 77. So here by mistake it is 54, but it is 64 raised to 37. Now we can see that this number is large, this number is large, so better to go for the Chinese remainder theorem. So dp is equal to d mod p minus 1, d is 37 mod p minus 1. 7 and 11 numbers are there, so 7 minus 1 is 6, 37 mod 6 is 1, then d mod q minus 1, 37 mod 10 is 7. Then we calculate 60 raised to 1 mod 7, because 64 is nothing but our cipher text, mod 7 which is equal to 1, and 64 raised to 7 mod 11. So here we can use directly the formula. So here actually it is 10, this is I guess copied from the previous, but we can easily calculate, don't consider this, but we can easily calculate 60 raised to 7 by 60 raised to 7 mod 11 by using the square and multiply algorithm, in which 7 is represented as 1 1 1. So all ones are there, so we are performing both operation multiply and the square and multiply operation, and initially we keep z equal to 1, and after every step we are at each step we are using the updated value of the z. So by mistake this is pasted from the previous slide. Now here we are getting the answer 4, and here we are getting the answer 1. So therefore we are getting the Chinese remainder equation as 1 mod 7, because this is with respect to mod 7 and this is with respect to mod 11, and second is 4 mod 11. So I have already published the video on the Chinese remainder theorem. So here we basically calculate capital M, then capital M1, capital M2. Capital M is 7 into 11, 77. Capital M1 is 77 by 7, and here it is 77 by 11. So we are getting exactly opposite values. Then we calculate this y1 is equal to this 11 inverse with respect to mod 7 and 7 inverse with respect to mod 11. That is nothing but what 11 y1 is equal to 1 mod 7 and 7 y2 is equal to 1 mod 11. Again we require to calculate the extended Euclidean. So here only we require to calculate only once, because we can attach the answer. Now here extended Euclidean for 11 7. So this is the way we can write down 11 is equal to 7 1 1 plus 4 7 4. Then we write down the equation. Actually last equation I forgot here again, but it is not useful. That is 3 is equal to 1 into 3 plus 0. As it is not required, that's why I have not written. So when we do this operation, we are finding out the extended Euclidean for this equation first, basically. That is 11 7, 11x plus 7y. So here with respect to 11 our value is 2, so therefore y1 is 2, and with respect to with respect to 7 our value is minus 3, but we again don't want minus 3 value. Therefore with respect to this, our mod is 11, so we are using 11 minus, that is negative mod. Negative remainder we convert it into the positive, so 11 minus 3 is equal to 8. So in this way y1 is 2 and y2 is 8. This is the Chinese remainder final equation to get the value of x. So this is the equation. So this, then we calculate m1, we calculate inverse. This is for the first, for the second 4, 7, and this y2 is equal to 8. And when we take the answer, so we are getting the answer as 15. So thus by this way we get again the original text, which is nothing but the 15. So in this way the RSA encryption and decryption is performed. So to perform the RSA encryption and decryption, the basic is that you should be able to find out the multiplicative inverse, and if the exponent and the mod value is large, then if you use the Chinese remainder theorem, the problem gets simplified. So to understand this RSA encryption decryption, you should be comfortable to calculate the multiplicative inverse and apply the Chinese remainder theorem. And these are the additional exercises you try. This is the 5th, 6th, 7th, and so sometimes they are giving directly n, and we require to calculate the phi of n, but this 119 is not that much big number, so we can try with the prime numbers. So in my previous problem, 7 into 11, 7 into 17, I guess that number is 119. So if we try some random numbers with the prime number, we can get this number. Similarly same for 247. These are the references. Thank you.